Dear viewers, Assalamu alaikum and welcome to the course of Wireless Sensor Network. Today we will be discussing about the sensor architecture and I am Dr.Zeeshan Bangash, Assistant Professor, Institute of Computing, Kohat University of Science and Technology. We will be talking today about the nodes, the wireless sensor nodes that are the central element in wireless sensor network, and it is through these nodes that the sensing, the processing and the communication take place. So we will be talking about its architecture and the different constraints related to these nodes. So first of all we will discuss the node architecture, as the nodes are involved in sensing, processing and the communication. So we will be discussing the node architecture. Then the node, we know that it consists of a sensing, processing, communication and power subsystem. So the designer have multiple options in deciding how to build. But putting together all these subsystems in a uniform and programmable node, so what are the concerns that are involved? What are the options we have? And these subsystems are basically the central element of a node. So the choice and the trade-offs that exist between the flexibility and the efficiency and the keeping in view of the energy and the performance constraints. So we will be discussing all these in this session. So let's start with the first agenda, and that's about the node architecture. So the node architecture, it's basically that the wireless sensor is consists of different subsystems and there are different integrations of the sensor nodes that are part of this wireless sensor network. So as I have already discussed that wireless sensor nodes are the central element of a WSN. So it is through these nodes that the processing, the communication or the sensing all took place through these nodes. So another important thing is that it stores, that these nodes particularly stores the communication protocol and the data processing algorithm. So whether it's an inductive sensor or a piezoelectric sensors or a resistive sensor, so it stores and execute communication protocols and also the data processing algorithm. So the quality, the size and the frequency of the sense data that can be extracted from the network, so they are all influenced by these physical resources available to the network, to these nodes. So the design and the implementation of these sensor node is of critical step. So as already discussed that there's some important parts that these nodes perform sensing and the communication and processing, and they have some power subsystems. So in the next slide we will be discussing an architecture of that node, that it comprises of some program that is written, some data, and then there is an analog to digital converter, and then there is different subsystems that are involved in the overall architecture. So we'll be discussing these things in the coming lectures. However, an architecture for a node is shown in the slide. So about the sensing subsystem. So the sensing subsystem, it basically integrates one or more physical sensors and it provides one or more converters, that is analog to digital converters, as well as there will be some multiplexing mechanisms in order to share them. So sensing is basically a physical phenomena and it is something that is not new. Most of the devices in past that are not new were using sensors. So this phenomena of sensing the so sensing any physical object is not new. So this sensing and about this microelectronics that are involved. So there are different sensors that are available in the market, and they are of very cheap prices. So some of the sensors that are available in the market has been shown in the slide. So you can just notice that the accelerometer and the different application area. So it's basically for 2D and 3D acceleration movement of a people objects. It basically detects the movement. So what this sensor is used? It's for noting down the volcano activities, or stiffness of any object, or irregularities in a rail. So that's easily available in the market and are very cheap. So there are some more different types of sensors. You can just it has been shown on the slides, so you can just read the details. So they are easily available in the market. Now, an important system, a subsystem in that sensor, that is basically the analog to digital converter. So a physical sensors it contains a transducer. That's basically a device that converts the energy from one form to another. So it's basically electrical energy. So the output of this device, this transducer, is an analog signal, and that needs to be converted to a digital signal. So an analog to digital converter is required in this sensing subsystem, and that must have a digital processor. So the figure shows that we have some analog signals, as we have discussed, and then there is an analog to digital converter, and why we need that we have already discussed about that thing, and then this converter converts it into a binary output. Now again, about this analog to digital converter. So it's basically a subsystem in a sensor. So it basically converts the output of a sensor, which is a analog signals, into a digital signal. We have already discussed that thing. However, this whole requires two processes. It's a two phase process. And the first phase is basically you need to convert that analog signal, and that analog signal has to be quantized. So what is this quantization? It's basically to convert, it is basically that you convert that continuous value of that signal into a discrete value. So discrete means both that are in terms of the time and in terms of the magnitude as well. And this is very important decision that determines basically the number of the values, the discrete values that must be allowed. And again, this analog and signal, and the second thing is basically the sampling frequency. However, when we are concerning about the analog signal, that needs to be quantified. So again, this quantification is again influenced by again two factors. And again, the first factor is the frequency and the magnitude of that signal. And the second factor is basically the availability of the processing and the storage resources, which is again a very important factor in wireless sensor networks. And for the second step or the phase in that conversion from analog to digital, it's basically the sampling of the frequency. So in communication engineering, or we can say that, and in digital signal processing, this frequency is decided by the Nyquist rate. So in wireless sensor network, however, this Nyquist rate does not suffix. So we need oversampling here in order to reduce that noise. So you can just see that the formula is shown on the slide, and this Q is basically the resolution in volt per step, and EBP is the peak to peak analog voltage. So M is the ADC's resolution in bit. So we will again be discussing these sampling frequency in the upcoming lectures as well. So about the processor subsystems, let's discuss some more detail. That the processor subsystem brings together all the subsystems, and again some additional paraphers as well. So its main purpose is to basically process the instructions that are pertaining to sensing or self-organizing, or basically pertaining to the communication. So it comprises of some non-volatile memories, some processing chips for store, and again an active memory for temporary storage, and an internal clock. So apart from these are some of the items that are part of that system. So let's discuss about the first architecture. So this is basically again the same thing I have already discussed, that it consists of some chips, some non-volatile memories, and some internal log. So this is basically the processor subsystem that comprise of. So let's look at the architectural overview. And basically this processor subsystem in a sensor network, that has basically consist of, or it should be one of the three basic computer architectures. We have already read about these architectures in computer architecture and assembly language. So the first architecture is the von Neumann architecture, second is the Howard architecture, and the third is the Super Howard architecture. So whether it is any one of so the processor subsystem can be designed by basically employing one of these three basic computer architectures. So you have to choose among these three one in order to design an architecture for a sensor. So let's discuss the first architecture, which is the von Neumann architecture. So what this architecture is all about, so you can just see in the diagram the architecture of von Neumann. So the von Neumann architecture provides is a single memory space, and that's used by both the programs instructions and the data, and it provides the a single bus to transfer data. So there's a single bus that is to transfer that data, and that data is transferred between the processor and the memory. So there's a single bus, and the architecture again has a very slow processing speed, because each data that transfers requires speed, requires each data that transfer requires a separate clock. So the architecture has a very low processing speed. So this is one of the limitation of this architecture. So again, the second architecture is the Howard architecture, and this Howard architecture, as you can see in the slide, that it is basically the modified version of the von Neumann architecture. And in this architecture, there are separate memory spaces for storing program instructions and the data. And again, each memory space is interfaced with a processor with a separate data bus. In the previous architecture, there was a single bus, and here there's a separate data bus. In this way, the program instructions and the data both can be accessed at the same time. So the additional feature in this architecture are that it supports special single instruction and multiple data operations as well, and a special arithmetic operations and a bit reversal addressing are also the additional features of this architecture. So that's about this Harvard architecture. So you can just note that it has some additional features as well, and it's an improved version of the von Neumann architecture. So let's talk about the third architecture, which is again an improved version of Harvard architecture. That's the Super Harvard architecture. So this super Harvard architecture is the next generation of processor architecture, and it's best known as with a reserve word SHARC, shark. And again, it's against the extension of Harvard system, and it has two additional components that the to its predecessors, and it provides an alternative for accessing IO devices from within the subsystem. And one of the component is the internal instruction cache that basically enhances the performance of the processing unit, so it can be used. So this super Harvard architecture, as you can see in the slide, and this again have two additional components. I have two components. That's the internal instruction cache, as I have already discussed, and again that enhances performance, and an underutilized program memory that again can be used for a temporary relocation place of the data. So it can be used temporarily stored frequency use instruction, thereby reducing the need for repeated fetching them again from the program memory. So moreover, this architecture is again the next generation processor architecture. So let's talk about the DMA facility, that direct memory access. It's costly. It is costly in terms of the CPU, CPU cycles that are involved in different task execution. And again, the program memory bus and the data memory bus, they are again accessible from outside the chip. So these are two extra features in this architecture as well. So again, it supports multitasking operating system, but it does not have the virtual memory protection mechanisms. So this is a extra feature and a limitation in this architecture as well. So let's talk about the second subsystem, that is the microcontroller. So this microcontroller is a computer that is present in a single integrated circuit, and this is basically it has been dedicated to perform one task and execute it one specific application. So these are some of the restrictions of this subsystem. And again, this microcontroller are integrated in many products and embedded systems. Today, such systems are elevators, or an office machine, or a ventilator, or a household appliance, or whether it's a toy. So this microcontroller is integrated in these products. So it's a daily use item, or the items we are using that are using this microcontroller. However, this microcontroller have some advantages, and again, it's, as you see that in the slide, that it integrates the different volatile memories and storage and EEPROM and PROM and discrete input and output, clock generation, and serial communication interface. So all of these are integrated in this this component. So there are some advantages and some disadvantages, and the advantages comprise of that it's suitable for building computation, and it's very less extensive. It's a standalone application, and because of its very compact and construction and small size, and it's very low power consumer, and it is available at very low cost. So these are some of the advantages. And one another advantage is the high speed of the programming and easy debugging because of the use of the high level programming languages. So this is second. However, this component have some disadvantages as well, and again, its efficiency, that is not so much powerful and efficient as the custom made processor like DSPs and FPGAs are. So this device is not as much powerful. And the second disadvantage is that some application might prefer to use architecturally simple but energy cost efficient processors. So it's not the choice. This component may not be the choice for them. So let's talk about the other subsystem, which is a digital signal processor. And you can just see that in the image a DSP has been shown. However, this processor basically processes the discrete signals with a digital filter, and this DSP is specialized microprocessor, and it deals with processing discrete signals with digital filters, and these filters minimize the effect of noise on a single or small or it may modify these spectral characteristic of a signal. This DSP is a specialized microprocessor, and it's basically built to perform some complex mathematical operation at a very extremely high efficiency, and it may be processing hundreds of millions of samples every second and providing real-time performance. So this is the scenario where these DSPs are used, and again, they're very much efficient, and they are basically designed with that Harvard architecture. So this is an important to note that these are designed using the Harvard architecture. However, another architecture, this is shown in that it has again some disadvantages. You can just note that's a powerful and a complex digital filter can be realized with the commonplace DSP. However, it's used for application that deploy for nodes in harsh physical reality. So there is where there's a lot of noise. So in that the DSP processors are used. However, they have some disadvantages that some tasks may require protocols that require periodical upgradation and modification, and that's a very resource constrained mechanism in WSNs in an ad hoc environment. So this is some of the disadvantage of this architecture or this component that's used in any environment. So let's talk about another subsystem. It's an application specific integrated circuits, and that can be customized for a specific application. And it's an integrated circuit that is customized. And there are two types of design, that it's either a fully customized or it may be a half customized. So there are two specific. So to understand the difference, it is useful to understand basically the building blocks of this subsystem. Let's talk about that. What is this full customized IC is basically. So there may be some logic cells and circuits or layouts that are custom made in order to optimize the performance. And the second thing is that it includes some features which are not defined by the standard cell library. And again, it's expensive in terms of the long design time. It takes very long time to design it. And the second design approach is the half custom ASICs, and they are basically built with the logic cells that are available in standard library. So in both the cases, the final logic structure is configured by the end user. So this reduces time to market, and financial risks are involved. So we need to financial risks can be reduced by eliminating the need to cycle through an integrated circuit. So an ASIC is a cost efficient solution because the interconnection as well as the logic structure can be specified according to the needs of the user. So this is also offered a great level of flexibility and reusability. So these are some of the good aspects. So again, it have some advantages and again some disadvantages as well. So let's talk about the advantages. That it's relatively simple and can be optimized to meet specific customer demand, and it's a multi-processor course that can be embedded and have an embedded software that can be designed in a single cell. However, it again involves a high development cost and lack of configurability. So this is again a concern. So they are basically not to replace microcontroller or DSPs, but to complement them. That is, you need these things in some specific scenarios. So to decouple these tasks from the main processing system, so they are basically used for this purpose. And about that field programming gateway, and basically this is more complex in design and flexible, and it's basically programmed electrically. That's basically to program by modifying a packet part, and that's done through support circuit diagrams and hardware description languages such as VHDL and Verilog. and they have again some advantages like high bandwidth, the flexibility, parallel, it supports parallel processing and works with a floating point representation, and again it's a very flexible in terms of the control, so it offers great level of flexibility. However, it has a disadvantage that the design and the realization process, the overall process, is very costly. And let's talk about some comparison. And the comparison is that working with microcontroller is preferred if the design goal is to achieve flexibility. Again, working with other mentioned option is preferred if the power consumption and the computational efficiency is desired. DSPs again are expensive, large in size, less flexible. They are best for signal processing with the specific algorithms. FGPAs are faster than both microcontroller and DSPs and support parallel computing. However, their production cost and the programming difficulty make them less suitable. And again, ASICs have higher bandwidth requirement. They are smaller in size, perform much better, and again consume very less power and than the other processing types. So they have a high cost of production, and the design process cost a lot. Dear students, these are some of the references from which the content have been taken, and you can just consult these references for further details. And thank you very much for patiently listening. Do subscribe our officially YouTube channel by clicking the bell icon. Take care. Allah Hafiz.